Funding for this year's rover was provided by the Yale School of Engineering and Applied Sciences, the Yale President's Fund, the NASA's TT Space Grant, and corporate sponsors like Alcoa.
Hi, my name's Alex Goss, and I'm the president of the Yale Undergraduate Rover Association. Before we get started on the rest of our video, I'd like to go over a little bit of the team structure that we have. Basically, our team is divided into 4 engineering sub-teams. We've got the electrical, the mechanical, the software, and the earth science teams. And sort of the way that our team is arranged, each of these sub-teams will complete team-specific tasks throughout the week. So for the earth science team, maybe that's doing research on different compounds that they might be looking for in the science-specific portion of the task, or for the software team, that might be debugging code. Now, in the rest of this video, we'll be looking at the different things that the sub-teams have accomplished throughout the year and how they've outfitted the rover in a way that will help us in the competition. Hope you enjoy.
For this year's rover, reliability was the name of the game for our electronics system. We have all of our electronics mounted on a modular aluminum sheet within the chassis, which is easily accessible through the hood. Let's take a look inside. The inside of the chassis is easily accessible through a Velcro Delrin sheet that is both secure and easy to get on and off. At the back end of the chassis, we have the rover's power distribution system. Here's our 25.9 volt LiPo battery connected in series with a key to start and an emergency stop. After the emergency stop, we have the voltage regulators. We have two 12 volt and two 5 volt voltage regulators for our motor control and other electronics. To power our drive motors, we go directly to a 25 volt bus. This bus distributes the power to the motor controllers here and here, as well as the motor. On the 12 volt end, we have our motor controllers for the actuators on the arm and various servos. We also have our cooling fans here, 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 and here. These help keep a consistent airflow through the chassis to keep it cool. Our communication equipment also runs off a 12 volt DC to AC inverter, which sends power over Ethernet through this cable outside the chassis to this radio here. Finally, on the 5 volt end, we have our sensor suite consisting of GPS sensor, methane, humidity, and temperature sensors on the end effector of the arm, as well as the main control system of the rover, the BeagleBone Black.
This year's rover was built with 3 principles in mind: versatility, accessibility, and practicality. Starting with versatility, we can take a look at the middle 2 wheels of the rover and see that they can be removed during tasks involving the arm to reduce the rover's weight.
Many of the problems we faced over the past 2 years involved our ability to manipulate the arm. Depth perception was a big problem for us last year, so we have introduced 2 more for a total of 3 camera feeds over our 2.4 GHz communication network. Most importantly, we have outfitted this year's rover with an arm that can be controlled via a master-slave arm system. The compatibility of the arm was improved by implementing a master-slave system in place of a standard Xbox controller. The master arm is a scaled-down version of the slave arm and is manually manipulated by the operator. The slave arm receives position readings from potentiometers placed in the vertices of the master arm. The slave arm reacts to these readings by moving until its own potentiometers match the positions of those on the master arm. This closed-loop analog feedback master-slave system allows easier and more exact manipulation of the robotic arm.
Lastly, we look at practicality. For the past 2 years, we have used a rocker bogie system for our suspension, which has fared poorly on the rock garden. However, this year, we're using an individual spring suspension for each of our 6 wheels.
Communication and control is an important aspect of any successful rover run at the URC. I'm going to walk you through our communication network and our command center setup. To start, we're using a 2.4 gigahertz MIMO network, multiple input, multiple output. At the base station, we have a 2.4 gigahertz sector antenna connected via Ethernet to our command computer. This sector antenna provides a wide range of signal as well as providing a solid frequency that will transmit our information and video without having line of sight issues. We have tested this up to 1.5 kilometers and it works perfectly. On the rover's end, it talks to another Ubiquiti M2 radio with 2 Omni antennas that can be found on a standard network router. Rover mission control consists of 3 main components. Number 1 is the controlling computer, which does our video and information processing. Number 2 is the controller. This controller is used to send position movements to the rover via our wireless network. It can also be used to select and read sensor data from onboard the rover. This year we have an extra 3rd component that we use to control the arm. This right here is the pilot arm. As you know from previously in this video, we have an analog feedback loop that allows for master-slave control of our robotic arm. As I move this arm, the potentiometers change their resistance value. In turn, this microcontroller processes that signal and sends it to our computer, which tells the arm to mimic this exact position.
This year, we have 3 major software systems. First, and most importantly, is the laptop that runs at the base station. It acts as the brains of the entire operation. Second, we have a BeagleBone Black on the rover, whose main goal is to relay motor commands from the base station to the motor controller, and also collect and aggregate sensor data for it to be sent back to the base station. Finally, new this year, we have a second BeagleBone Black at the base station, whose goal is to read input from the dummy arm so it can be relayed to the base station, who can convert that into motor values to relay onto the rover. All of our software, like last year, is written in Python. From last year, we had a very, very reliable and stable system. However, we had a fair number of problems. This year, we've been building on last year's software instead of replacing completely, and focusing on making the rover much easier to control. Second, there have been a few new sensors and new cameras added to the rover, whose job it is software to integrate. And finally, the dummy arm also needs to be integrated in software. As we said, we're reading analog input on the new BeagleBone Black, transferring that to the base station, who converts all of the analog signals into motor values, which are then relayed to the rover in order to move the arm.
Overall, the capabilities outlined in this presentation should provide us with enough to successfully complete any task presented at the URC. For example, in the terrain traversal task, we have adjustable independent spring suspension on each wheel. This allows us to adjust the height and breadth of the chassis, which will be very helpful in clearing lots of different obstacles. Additionally, the tires we are using this year have an extensive amount of tread, but are also soft and pliable. This allows for good traction on sandy or hard surfaces, particularly in the rock garden. For the astronaut assistance task, we will be utilizing our GPS sensor to track, map, and locate downed astronauts. To deliver the tools to them, we will be able to use our extended chassis to place tools in a basket with our newly designed arm. This should allow for speedy and easy operation. For the equipment servicing task, the dexterity of our newly designed master-slave arm system will really come into play. Last year we were having lots of issues with depth perception, so we also added 2 more cameras mounted under the chassis and on the arm, in addition to the final camera at the rear of the rover. This will allow for accurate and precise movements, and hopefully it will allow us to successfully complete the equipment servicing task.
My name is Maddie Hoffman and I'm a freshman chemistry major here at Yale, and I am the head of the Earth Science sub-team. So for our science plan, we started out by conducting research on Mars and Utah. And so what this consisted of was looking a lot at NASA's website and also the U.S. Geological Survey website for Utah. And then from here, looking at these press releases and information about the different missions and rovers and the geology of Utah. We would also look at scientific research papers. A lot of the papers we looked at and read were published by JPL. We also consulted Professor Michael Faison of the astronomy department here at Yale, who gave us information about the astrobiology of Mars because he teaches a class on the search for extraterrestrial life. And this research was all done to gain a more in-depth understanding of the science of Mars, mostly biology and geology. And those sorts of processes. And from here, we were able to decide on what we wanted to do during the science task at the competition. So a lot at the beginning of the year, this consisted of picking what tests and instruments we wanted to include on the rover. This year on the rover, we have a humidity sensor, a temperature or a thermometer, and a methane sensor.